discuss linear algebra. As a just review, today I will discuss different type of question which had come different type of competitive exam. Actually, today's goal of this lecture is, as a review I will discuss all this question. My first question, which had come CSIR net 16 December 2022. This question is obviously very basic question. The question is, suppose A is a real n cross n matrix with rank R and V be the vector space of all n cross n matrix such that Ax equal to 0. That means V contain all n cross n matrix which is such that Ax equal to 0. Actually, this is nothing but this is actually null space. We all of us know this is the definition of null space. Then my question, what is the dimension of this vector space? That means we have to find dimension of this null space. Since we have to find dimension of null space, for this consider a linear transformation which is denoted as TA MNR to MNR such that T of x equal to Ax. And we all of us know this type of linear transformation. If T be a mapping from Fn cross M to Fn cross M, where F be a field, such that T of x equal to Ax, where A be n cross n fixed linear transformation, then we all of us know rank of this linear transformation is M times rank of A, and nullity of this linear transformation is M times nullity of A. Similarly, trace of this linear transformation is M times trace of A. To find dimension of null space, here I will apply rank nullity theorem. We all of us know the rank nullity theorem. Rank T plus nullity T equal to dimension of V. Here we have to find the nullity T. Therefore, by this theorem, rank T would be n times R plus nullity T and dimension of V equal to n square. Therefore, that imply nullity T equal to n square minus nr. I hope my all viewers have understood how we have to find dimension of this type of linear transformation. One question based on bilinear transformation. The question is, consider one matrix. Given matrix is such type which belongs to M to R. Now consider one transformation which is bilinear map such that phi R2 cross R2 to R, which is defined by phi V equal to V transpose AW. Then choose the correct statement from below. Option 1, phi V W equal to phi WV. This is true for all VW belongs to R2. That means we have to prove this transformation is symmetric. Option 2, there exists a non-zero vector V belongs to R2 such that phi VW equal to 0, and this is true for all W belongs to R2. Option 3, there exists 2 cross true symmetric matrix B such that phi of U comma V equal to V transpose BU. Therefore, the map which is denoted by psi and which is defined from R4 to RR, defined by psi of V1 V2 W1 W2 equal to phi of V1 V2 times W1 W2. Is this mapping is linear? This question is basic question, but to define this question elaborately, at first I will define what is the bilinear map. As a review, at first I will discuss some property of bilinear form. Consider the mapping which map from BW to one real number BUV, and this is actually notation of bilinear form, but in the question the bilinear form is defined as phi PU. This is not matter actually, since the name is bilinear form, so this is the notation is BUV. Bilinear form, this is actually, this definition I have defined in my previous video elaborately. Today's topic is just as a review. Bilinear form means this is linear with respect to first component, and this is linear also with respect to second component. That means bilinear form means this is linear with respect to both component, and bilinear form define vector space cross vector space to R. So define a mapping VW to B of UV means one real number, and this mapping is symmetric when VW equal to BWV. This is true for all VW belongs to the vector space V, and this is skew symmetric when BVW equal to minus BWV, and non-degenerate. Non-degenerate means such vector V in the vector space V such that BVW equal to 0, and this is true for all W belongs to vector space, and that imply our chosen V always would be 0. This is the definition of non-degenerate. And degenerate is there exists non-zero vector V and W such that BVW equal to 0. The idea of non-degenerate means actually matrix representation of this bilinear form with respect to basis always would be non-singular, where the matrix A is such type A equal to Aij, where Aij equal to inner product Ui Uj. And this is actually definition of actually positive definite matrix. Now let's come back our original question. Notice the question. Phi of VW equal to V transpose AW. That means this is actually quadratic form, and who is defined as phi of VW equal to V transpose AW. Just put the value. Then this would be V1W1 plus 4V2W1 plus 2V1W1 plus 3V2W2. Phi of VW equal to phi of WV, and this is true for all VW belongs to R2. This is actually notation of symmetric when bilinear form is symmetric. Notice here the given matrix A with respect to this quadratic form is not symmetric. So this bilinear form phi of VW equal to phi of WV, this cannot possible because their given associated matrix not be symmetric. Also mathematically, notice this is the phi of VW, then phi of WV would be W1V1 plus 4W2V1 plus 2W1V2 plus 3W2V2. Here not W, and here would be W2, and 4V2W1 plus 2V1W2, and here 4W2V1 and 2W1V2, this is not same. So mathematically phi of VW not equal to phi of WV. That means option 1 is a wrong option. Option 2, there exists a non-zero V belongs to R2 such that phi of VW equal to 0 for all W belongs to R2. Here this is actually the idea of non-degenerate. Here there exists a non-zero vector such such that phi of VW equal to 0 for all W belongs to R2. That means this non-zero vector is orthogonal to entire R2. But since with respect to this quadratic form the associated A is not equal to 0, that means this is true when phi of VW equal to 0, that means one vector which is orthogonal to whole entire R2. This is true when only V is trivial. Recall the definition of non-degenerate. This is true when V equal to 0. And non-degenerate means actually the matrix representation of this bilinear form with respect to basis. When this matrix would be non-singular, then obviously this bilinear form is non-degenerate, and this is true when V equal to 0. So that means option 2 also wrong option. There exists a non-zero vector V belongs to R2 such that phi V equal to 0 for all W belongs to R2. This is wrong option because this is true when V is trivial. There exists non-zero V which is orthogonal to whole R2, whole entire space. This is not possible. And notice option 3. Option 3 indicate there exists 2 cross 2 symmetric matrix B. One another symmetric matrix B such that here the quadratic form is such type phi of not V comma W, phi of V comma V is equal to V transpose BV. For this, notice here, given phi of VW equal to this quadratic form, then phi of V comma V would be V1 square plus 4V2 V1 plus 2V1 V2 plus 3V2 square, which is equal to V1 square plus 6V2 V1 plus 3V2 square. And from this quadratic form, we can generate one matrix 1 3 3 3, which is actually symmetric matrix. Actually, given idea is here actually this theorem has used. If A be matrix representation of an inner product space with respect to basis, then always I will get inner product UV equal to U transpose AV. And this A always symmetric because in inner product UI UJ equal to UJ UI. This theorem we can tell option 3 also right option. There exists a 2 cross 2 symmetric matrix B such that phi of V comma V equal to V transpose BV. And this symmetric matrix is such type equal to 1 3 3 3. Option 4 indicate the map psi from R4 to R which is defined by psi of V1 V2 W1 W2 equal to phi of V1 V2 comma W1 W2. And this type of map is actually linear map. This option is also wrong option because the mapping is psi from R4 to R4 such that defined mapping psi of V1 V2 W1 W2 equal to phi of V1 V2 comma W1 W2. And phi of V1 V2 comma W1 W2 is means this quadratic form. We have to prove is this quadratic form is linear. For this, psi of alpha V1 alpha V2 alpha W1 alpha W2 equal to alpha V1 times alpha W1 plus 2 alpha V1 times alpha W1 W2 plus 4 alpha V2 times alpha W1 plus 3 alpha V2 times alpha W2, that equal to alpha square times V1 W1 plus 2 V1 W2 plus 4 V2 W1 plus 3 V2 W2, which is actually alpha square times psi V1 V2 W1 W2. That means I have got psi of alpha V1 alpha V2 alpha W1 alpha W2 equal to alpha square times psi V1 V2 W1 W2. That means If this is linear, then this equal to alpha times psi of V1, V2, W1, W2. But here I have got alpha square times psi of V1, V2, W1, W2. So this mapping is not linear mapping. I hope my all viewers have understood this type of concept easily. That means option 4 also wrong option. Only option 3 is a right option. Today I will stop here. In my next video, I will discuss this type of question elaborately because linear algebra actually very important topic for competitive exam, also for higher study. So, in my next video, I will continue this topic again. See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel for more videos. Thank you so much.